This video will be talking about E1 and E2 reactions. These reactions are both elimination reactions and they're very helpful for forming alkenes. In both E1 and E2 mechanisms, a proton is lost or eliminated and a carbon-carbon double bond is formed, which is the alkene. In E1 reactions, the rate-limiting step only has one molecule involved, which is how it gets its name. It's an elimination reaction, so E, and it's unimolecular, so 1. Ionization of a molecule happens first, which is our rate-limiting step, to form a cation. After that, the molecule is deprotonated by a weak base and an alkene is formed. It requires a good ionizing solvent, such as an alcohol or water, and rearrangement of the product can occur, which lends itself to Zaitsev's rule. Zaitsev's rule states that the product of an elimination reaction will be the most stable alkene or the most highly substituted. This results in a favor of trans products versus cis ones. Here we can see the different levels of substitution, which will relate to the more stable molecules. So on the left, we have our most substituted molecule, our tetra-substituted, which will also be our most stable. We then have our tri-substituted, our di-substituted, and our mono-substituted. In this example, we can see our first step where the ionization to give the carbocation and chloride and the weak base deprotonates to give alkenes. In this bottom portion, we can see that this bond will break, and as well as this one, and this will form a bond with the oxygen, the hydrogen right there, which will give our product right here. Both of these will be di-substituted. But again, the trans version will be favored. In this example, the oxygen will form a bond with this hydrogen. The bond between this hydrogen and this oxygen will break and the atoms will go to the oxygen. And then over here, we will have the atoms from this bond join the oxygen. And here we will have the bond between our hydrogen break and the atoms will form here. And this oxygen will bond with this hydrogen. This will give us a major product and a minor product. E2 reactions are pretty similar, but they are bimolecular elimination reactions, which once again gives it its E2 name. It's a reaction where bonds break and new ones form at the same time in one step, so there is no rate-limiting step. A strong base is required to take a proton on a carbon atom that is adjacent to the one with the leaving group. After that, a double bond forms as the base takes the proton and the leaving group leaves. The proton that is taken must be trans and coplanar to the leaving group in the transition state. Zaitsev's rule will also apply to E2 reactions unless the base and or the leaving group are bulky. The use of small unhindered bases favor the Zaitsev product, or the more substituted alkene, over the Hofmann product, which will be the less substituted alkene. The stereochemistry of the starting material can result in the Hofmann product forming over the Zaitsev one. In this example, we can see that the strong base takes a proton on the carbon next to the leaving group, and the leaving group leaves to give an alkene. So down here, we will have a bond between this oxygen and this hydrogen. The bond between the hydrogen and the carbon will break to form a double bond between the two carbons, and the same thing will happen with this side. And this chlorine will be our leaving group. This will give us our minor or mono-substituted, product and our major or disubstituted product. The major product is disubstituted because it is more stable. In this example, we have our bond formed over here between this oxygen and the hydrogen. Our bond between our hydrogen and our carbon will break. And this bond will go here, forming our double bond. The chlorine will leave. This hydrogen will form a double bond here. And this hydrogen will attach to this oxygen, resulting in our minor product and our major product. Our minor product is disubstituted, and our major product is trisubstituted.